Today we'll be discussing Thevenin's theorem, how to apply it, and its significance in circuit analysis in our world today. Thevenin's theorem allows for the reduction of complex open terminal circuits to be reduced into a much simpler form. The Thevenin equivalent voltage and resistance to the left of the open terminals is equal to the voltage and resistance of a load-bearing resistor. Using Thevenin's theorem, any two-terminal DC network can be reduced to an equivalent circuit consisting only of a power supply in series with a resistor. The resistor is the summation of all individual resistances to the left of the open terminals. If the summation is done correctly, the value can be used to find the voltage across and current through the load-bearing resistor. To calculate R Thevenin and E Thevenin, temporarily remove all components to the right of the open terminals, including the load resistor itself. Identify and mark both terminals. To calculate R Thevenin, simply sum all resistances around the circuit. This is done by simply using the summation of resistance formulas I'm sure you're all familiar with. As you can see by my calculations, the resistance, or the R Thevenin of this circuit, is 15.3 ohms. E Thevenin is simply the voltage across the resistor in parallel with the load-bearing resistor of interest. This is used because, as I'm sure you're aware, voltages are common across parallel elements. E Thevenin is simply R2 multiplied by E1 divided by R1 plus R2. For this circuit, as I'm sure you can see, 4.62 volts is found to be the E Thevenin. IL is, or the current through the resistor, is then found by simply dividing E Thevenin by R Thevenin plus the value of the load-bearing resistor itself. Thevenin's theorem is a highly significant process for circuit analysis and allows complex networks to be simplified and analysed. Once Thevenin equivalent values have been determined, it is now possible to investigate the effect of changing the values of components around the network and how they affect the behaviour of the circuit. This is incredibly useful because complex calculations do not have to be made for each change. It has also allowed for the analysis of networks with sources that are neither in series or parallel, and has allowed for the reduction of the number of components to establish the same behaviour at output terminals. Although the example I showed you today was fairly simple, the same concepts can be applied to much more complex circuits. I hope this video has given you some information about Thevenin's theorem, how to apply it to circuits, and how it is incredibly useful for circuit analysis in our world today. Thank you.